And for question 6, we are discussing about the perfect shuffle. So a perfect shuffle is, first we assume we have even number of cards. And we divide the cards into 2 equal parts. And then we go the lower part first, and then the upper part, the lower part, upper part, lower part, upper part. So for this instance, if we have 6 cards, and number 1, 2, 3, 4, 5, 6, then after one perfect shuffle, we get 4, 1, 5, 2, 6, 3. So for part A, we want you to argue that when we perform perfect shuffle enough number of times, the card within the deck will resume the initial ordering. That is 1 to 2n from top to bottom again. So first by observation, the first half of the card, 1, 2, 3, will go to position 2, 4, and 6. So the first part, their position will times 2 after one shuffling. And for the later part, n plus 1, n plus 2, n plus 3, it will go to 1, 3, 5 all the way. And by observation, we can say, so let's say some card is at the position AT after T shuffles. And by observation, we can say after one shuffle, we can get its new position by times E with 2, and then modulo 2n plus 1. So for example, n plus 1 times 2 is equal to 2n plus 2, and mod 2n plus 1, which is equal to 1. So it goes from n plus 1 to 1. And therefore, after T shuffles, let's say its initial position is A0, then its new position is 2 to the power T times A0. So we know that GCD 2 and 2n plus 1 is equal to 1. And by Euler's theorem, we can say 2 to the power 5 2n plus 1 should be congruent to 1 modulo 2n plus 1. That means after 5 2n plus 1 shuffles, its new position is 2 to the power 5 2n plus 1 times its initial position, which is congruent to its initial position. So this is one of the possible number of shuffling we can get it back to the initial position, but this is not guaranteed to be the smallest number of shuffling. So for part B, we ask you what is the minimum number of perfect shuffle to resume the initial ordering. So it becomes a little complicated actually. So first we talk about the multiplicative order of B modulo n, which means if B to the power E is congruent to 1 and E is the smallest possible positive integers, it happened, then we call it it's a multiplicative order of B modulo n. So what we want is the multiplicative order of 2 modulo 2n plus 1. And we can write it as this order 2n plus 1, 2, this function. So I didn't find a very beautiful algorithm or closed form to compute this value, but the interesting thing is this is an online encyclopedia of integer sequence by Sloan. So as far as I know, he also has a physical book of such physical version of such encyclopedia. But this is here the sequence A002326 is the contains the number we want. But I also prepared a property that doesn't help much for this, but I just find it interesting and it's related to group theory. But this is not formal definitions. No, so first we consider A equal to B if A is congruent to B modulo 2n plus 1. And A be the set that contains all the numbers we would normally count in phi 2n plus 1. So A and the multiplication operation forms a group. And we also get the set B, which is equal to S, all the possible 2 to the power n, and under modulo 2n plus 1.
I think the upper index should be 2 to the power j.
It will be confusing, yes. For some j. And we can check in the property of these two. They are both groups, and B is a subgroup of B and multiplication is a subgroup of A and multiplication. So we are back to Lagrange theorem. So the size of this B is the order of this group is the multiplicatory order we want to find, and this is phi 2n plus 1. So maybe we can get the order is actually a factor of phi 2n plus 1. And by the way, this group A and multiplication is called the modular multiplication group. But this is not the formal definition of it. But it's a nice property too. Maybe help us a little to find this value.
So for instance, let's take a simple example. So in our case, we have 6 cards, right? 1, 2, 3, 4, 5, 6, right? So let's start. Okay. So if you focus on card 1, the next step that it will move to position. So at the beginning it is a position 1, right? Sure. That's okay. After one step, it will go to position. So let's say this is position 2. Is that okay? Because it's 2 times. After another step, it will go to position 2 squared. After one step, it will go to position 2 cubed. But then always we are going to, because we are considering 6 cards, so we are always considering mod 7. Is that okay? Is that okay? So we know what? We know that if we continue to do this, after 6 steps, it will go to 2 to the power 6 mod 7, right? And because 2 and 7 are coprime, they don't have common prime factor, and then 7 is a prime. Okay, in this special case, we know that 2 to the power 6 is equal to 1 modulo 7. Am I correct? So it is guaranteed that after certain steps, it will go back to the original position. Okay, but on the other hand, this is not necessarily the minimum number of steps that we need. So if you look at the numbers, so after one step, you go to position 2, right? After 2 steps, you go to position 4. After 3 steps, you go to position 8. But then you are modulo 7, right? 8 will be equal to 1 modulo 7. So actually, if you have 6 cards, to do the perfect shuffling, only 3 shuffles, you resume the original order. Is that okay? So what Simon says is that, okay, if you consider all the numbers here, all the 2 powers here, so the collection of them, it will form a subgroup. Subgroup of what? Subgroup of the order of, or the numbers, the subgroup of those numbers that are coprime with 7. Is that okay? Or coprime with 2n plus 1. Okay, so in that case, that's why the order, the minimum cycle length, must divide the phi of 2n plus 1. Because phi of 2n plus 1, you guarantee you get a 1. And then for some small steps, you can get 1. So this length must be a divisor of the whole length. Because you want the 1 to repeat enough number of times, you can get the 1 again. So one must divide the other. Is that okay? Okay, now, there are 2, so here, this is the rifle shuffle of this form. You get 1, 2, 3, 4, 5, 6. So you put the bottom to the top, and then one after the other. So you transform it to 4, 1, 5, 2, 6, 3. Is that okay? So you can define a different types of shuffle. Okay, so a different type of shuffle may be like this. So let's shift rather than this one. This part is still on the top, that part is still on the bottom. So you get 1, 2, 3, 4, 5, 6. And then after a shuffle, then this time, this is a second type of shuffle. Then you will get what? You will get 1, 4, 2, 5, 3, 6. Is that okay? And then you can still argue how many times do we need to resume the original order. We know that we must be able to resume the original order. Because it's a kind of a pigeonhole principle that you must have cycles. So if you look at 1, 1 goes to 1, and 2 goes to 4, or 4 goes to 2, and then what else? And then okay, so actually, if you know how to solve this problem, you should be able to solve this problem. This is the same. This here, each position, each number is mapped to 2 times of that position modulo 2n plus 1, right? Here, what is special? It's like the 1 and the 6, you never move. And then it is the middle cards that are moving. Am I correct? Yes. So this time you are moving to what? 2 times the original, but in that sense, so you relabel this as 1, 2, 3, something like this. Okay. It's 2 times the original modulo 2n minus 1. So rather than 2n plus 1. Because you have two fewer cards than in this case. Yeah, go home and check this one. But I find it the most. So there is one more type of shuffle that we can do this. I forget the solution, but it's a long time ago. So this time it is like 1, 2, 3, 4, 5, 6. You put 4, 5, 6 here, reverse, upside down, and then put that back in. Is that okay? Okay, so you get what? You get 6, 1, 5, 2, 4, 3. And then you can still ask how many times do you need to get back to the original. Okay, these are some interesting facts. And then, okay, rival shuffle is actually performed quite often. So if you go to a casino, so people will do this, right? Okay. Or if you are playing the bridge game, we also normally shuffle the cards like that. But of course, we do not do perfect shuffle. It's not always one after the other. So sometimes we do 1 and then 1 or 2 and then 3 and then 1 and then 1 or 2 and something like this. Okay. So some time ago, I think within 10 years, I hope. So there is an article in a newspaper that says how many shuffles do we need so that the cards should become random distributed. Okay. So or how do you define what is meant by random? So random could be defined as the average distance. So you do the shuffle like this, always in this form. There is a model of like, on average, it is like, or in most of the cases, it is 1 card. Or in some few cases, it's going to be 2 cards inserted, or 3 cards, something like this. So there is a kind of a distribution. And then, yeah, let's guess. Okay, so in normal daily life, so how do you what is meant by random or random enough? So it is to define the distance between a card in the outcome and the position of the card in the original. The absolute distance of each card, you sum them up. You want to make this as large as possible, so it looks like random, right? Okay, so let's guess how many shuffles should be optimal. You don't want to shuffle a lot of times, because if you shuffle a lot of times, you probably get back to something that is not as random. Guess. 3, 5, 10, 7. Okay, so go home, yeah, or if you are interested, go to the web and check. So the magic number is 7. Okay, 7 shuffles is enough. Okay, 7 shuffles to make the cards random. Okay, so there is a mathematical model on this one, and they explain why 7 is the best choice. Okay, and it agrees with our daily life. Usually, when we want to make the cards not as random, we shuffle less than 7 times. Okay, but on the other hand, we want to make the cards that is like very normal. So in the bridge game, so normal. What is a card that is normal? So you will roughly have 3 cards in each suit, roughly, because there are 13 cards. Okay, so what is not normal? So maybe you have 8 cards or 9 cards in one of the particular suit, then it's not normal. So if you want the cards that is distributed that looks like a normal hand, which has roughly 3 cards in each of the suits, then you should shuffle around 7 times. On the other hand, if you don't want to do that, you don't do rifle shuffle, or you shuffle like 3 times, then it's normally random. Okay, thanks all. So let's end the class today, and then we will have our exam on Tuesday. Okay, remember it's Tuesday. Okay, the scope is just.
And please remember calculator.
Oh yes, bring your calculator.
But do not use cell phones.
Okay, no Wi-Fi, no internet access. Okay, yeah, no mobile access. But bring a traditional calculator that allows you to do what? To do modular arithmetic, and then do
some calculation.
Some power or whatever. Okay. Okay. By the way, I hope you are using. So how do you, okay, so here it's like 11 is the decryption key. So you want to compute 70 to 11 like modulo 2419, something like this, right? How did you do that? Yeah, 11 is not a large number, okay. So each time you multiply 70, you mod immediately, so that you don't want to get the number very large. Remember, we are doing modular arithmetic. You can do modulo operation at any steps. Okay, so you get 70 times 70. Okay, some kind of large, maybe. Or if you don't think it's that large, okay, you can multiply 70 again and multiply 70 again. Okay, that's large now. So you modulo 2419, you reduce the number to a smaller number and continue to multiply 70. Is that okay? Is that okay? So, or if you are clever, very clever, I don't know. Because 11, you can still use kind of a binary operation. So you have 70, you multiply it, okay. Then you square it, then you get 70 to the power 4. And then you square it, you get 70 to the power 8, right? And then you take modulo, and then you need to multiply 73 more times, and then you get your answer. Is that okay? So it's a shortcut when the number is small. So we will not, also hopefully we will not give you a very large number for decryption. Yes, so hopefully.
So in my experience, when I encrypt the question,
yes.
I just type in something to the power 211, then it overflows.
Oh, overflows. Okay, and don't worry about doing the factorization of times. We will give you the time factorization. So for this homework, 2419, you have plenty of time. Then we give it as a task for you to find out 41 and 59. In the exam, we will tell you what are the 2 primes that constitute the modulo n, the n. Okay, so don't worry about that part.